This video is going to cover the portal method for approximations. So how the portal method works is that we're looking for the inflection points, and at the inflection points in the deflection or elastic curve, that's where we're going to have zero moment. So at a pin, we allow rotation. So with this load, we're going to have pins like that. And then for our point load, he's going to go up and then he's going to go down, kind of something similar to that. So our inflection point is right here and technically down at the pins. So these are supposed to be at right angles as much as humanly possible, but my drawings are not the greatest. But that is what it looks like. So at inflection points, we assume zero moment. That's one of our big assumptions that we're going to make for the portal method. For a fixed end, the inflection point is at the middle. So it's at the mid height for fixed columns, which is effectively the same thing that we got going on here at CD. The inflection point is right at the middle. So if it's a pin end, then it's going to be at the pin. Obviously, there's no moment at the pin, but if it's fixed, it's going to be at the middle, at the mid height, mid length, whatever it's going to be. The second assumption that we're going to make is that we're going to share column shear. So we're sharing our column shear. So how it works for a basic bay that we have here, let's say this bay is 10 feet wide, and let's say it's 12 feet tall. What we're going to do is we're obviously going to make our free body diagram cuts where we have zero moment so that we can actually solve for this. I'm going to be really lazy though, and I'm not going to draw it all the way down. So we're going to assume that this is 12 feet, even though it's tiny, and that this is 10 feet. And we've got our 450 pound force here at the end, which is D. So when we make those cuts, and of course this is totally not to scale, we're going to have shears, internal shears at those cuts. And so we effectively just cut here and here. Now for each bay, they're each going to have one shear. If you had a second bay that was right next to it, then you would have an additional shear, which makes the interior bays a total of 2 shears if there are multiple bays. The ends still get 1, but the middles get 2 because, again, with superposition, they would get twice as much. So we're just going to kind of ignore that for now, but the more you know. So what we're going to do with this column shears, we're going to assume that each one of these V's, each one of these shears is the exact same value proportionally. So if it's 1 V, then it's just 1 V. If it was 2 V's, then it's obviously twice the amount. So if we just sum the forces in the X direction here, we've got 450 pounds positive minus one of those V's minus another V. Again, V is the same exact variable. So we're going to get that V is equal to 225 pounds. So each one of these V's is 225 pounds. Next, what we're going to do is we're going to analyze our side D. So if our inflection point happens right here at the middle, if that's the inflection point, then we're going to just look at the 5 feet over here to the left. So we're going to draw a new free body diagram just for D. So again, he's a total of 12 feet tall, but this time only 5 feet wide. We did find V over here to be 225 pounds. We have our 450 pound load actually at spot D. And then when we made our cut, we have our shear force. This is shear in DC, and this is our normal force also in CD. So we made that cut right at that inflection point. So what we're going to do is we can sum the moments actually at D. If we sum the moments at D, and yes, sure, there technically would be a y down here. But if we're summing the moments about D, AY is not going to act, and nor is the normal at C, or normal of CD. So technically, the only loads that are going to be acting here are our 225 and our shear. So now we're going to get our shear value. So if we sum the moments about D and set it equal to 0, we've got our 225 going the wrong way, so minus 225 times his distance of 12 feet up to D. Then we still have a negative shear of CD times a distance of 5 feet. He's also going negative, he's also going the wrong direction. So we're going to find that shear CD is equal to negative 540 pounds. Okay, so what does that do for us? Well, now if we actually want to find the moment at D, we're talking the internal moment. So what we're going to do now is we're going to make a cut right here and analyze just this half of our free body diagram. So we're going to make that cut for D. Again, he is 5 feet wide. We just found the shear CD, which was negative, so technically he's going up. So 540 pounds, then there's technically normal CD here. And we just made that cut, so technically there's a shear and a normal and a moment at D. So we want to find that moment at D. So conveniently again, if we sum the moments about D and set it equal to 0, well, there's moment at D acting there. He's of course going the wrong direction, so there's negative moment at D. Normal CD here, he doesn't actually act at D because he's in line with it. So then it's just the 540, and he's going to be going the correct direction. So plus 540 times a distance of 5 feet. So moment at D is equal to 2.7 kip feet. So that was D. Now technically we also wanted moment at C. So moment at C is literally the same. Just look at it, he's flipped. We already found our shear and normal at the middle, so we can literally just draw our 5 feet going the other way, where we slice into it. We have shears, we have normals, and we have moment at C. And of course, remember, if it's going up on the left side, it's got to be going down. So this is down 540. And if it's going to the right, it's got to be going to the left. So this is normal CD. So again, all we got to do is sum the moments about C, set it equal to 0. We got moment at C is actually going positive, and so is the 540. So plus 540 times 5, so we get that moment at C is equal to negative 2.7 kip feet. So if we wanted to draw our moment diagram for this guy, our moment diagram would be positive 2.7, 0 at the middle, and negative 2.7. So assuming I could draw the straightest of lines, would be 2.7 kip feet and negative 2.7 kip feet. That would be our moment diagram for member DC.